Hey, it's Mr. K doing a video for AP Physics 1 and 2, talking a little bit about resistivity, resistance, and all that stuff. And so let's start off by proposing a question. I already have these diagrams up here, but let's say you are a little electron, little charge carrier, and you are with your charge carrying buddies. You're in a big pack, let's say like 30 or 40 or 5 million of you, and you got to make it from one side to the other of a wire, or maybe this is like a hallway. And it's long, it's narrow, it's super thin. You got to go one by one by one by one and single file it through this hallway. And maybe there's these twists and turns that you got to make to get to the other side. Well, it would be very difficult for you to make it through quickly. On the other hand, you have an open hallway, very open, wide, a lot of room to walk around, like the cafeteria hallway. And it's very easy for all of you to move through all at once. In fact, this hallway, it's not only wide, but it's also short. And so the story here is that resistivity deals with the geometry of the thing you're trying to move through. Both of these things would be conductors, but this one is much easier for a current to flow through than this one. All right, and not only that, we need to worry about what that material is. If you have copper, copper is a great conductor. If you have pencil lead, it's not as good a conductor, but it will still conduct. It's a semiconductor. Well, not pencil lead, but graphite. And the temperature also matters too. So if your material, imagine this material is all these molecules are in the way of these electrons trying to flow through. If that material gets hot, those molecules are now vibrating and maybe even rotating around potentially. And that makes it harder for the electrons to move from one side to the other. And so, go to your bathroom, look above your mirror. You probably have a filament light bulb there still. And when you turn your lights on, that filament light bulb will first heat up and it'll start to glow. Then it glows very, very brightly. And you turn your light bulbs off, or you turn the power off, and the light bulb is still glowing with an orange there. And so what happens is that the current tries to flow through, and as it flows through, the resistance just shoots up due to the temperature change. And those light bulbs get really, really hot. And so we can talk about resistivity of the material based upon resistivity of the material based upon the properties of what that material is like and the temperature of it. But we're also going to be we're mainly going to be concerned here with AP Physics 1 and 2 with how resistivity would provide this thing that we call resistance. And resistance is going to be that thing that gets in the way of current trying to make it through a circuit. And as your resistance rises, as it gets bigger, that current will have to probably slow down and less charges can flow by per second. But you're going to try to drop off a little bit more energy based upon how that resistance is set up. And we'll cover that whenever we start to do simple circuits. So resistance, a little bit different from resistivity. Resistance relies on resistivity, is equal to the resistivity. Usually you draw like a row of that, it's like a density of stuff. And then it's going to depend upon the geometry of these. So before I write down the rest of this equation, let's take a look at your resistivity or resistance with these two shapes. And what we said earlier is that the one that was long and skinny, that would provide a bit more resistance to you than the one that was shorter and fatter across. And so it turns out that with resistance, we would take the resistivity, which is a property of the material. I'm gonna put a picture of a table of resistivities on this video. But the longer the thing is, the more crap there is in your way, the more stuff there is for these electrons to run into. And so the L, the length of the thing, would be on top of this equation. And it turns out that on the bottom, you're gonna have the area that you are trying to work with. So here we have a big pipe, here we have a small skinny pipe, and so the small skinny pipe would have an area that was much smaller, and so as A went down, resistance would have to go up. Okay, so for resistivity, again, you're looking at, that's the property of the material that you're using. You're using copper, you're using silver, you're using gold. Those are really, really great conductors, low resistance. But you have other ones that are kind of higher resistance, but not really that high of an insulator, and those would be like semiconductors. And then you got insulators like rubber, where resistance is super high per unit length. And so this equation is a very simple equation, but if you notice that if we were to take this rod or this copper cable, this copper wire, if I were to chop it in half, well, what would happen to your resistance? Okay, and so looking at that, if I were to chop this copper wire in half, your resistance, if L was cut in half, should go down by a half. If I were to chop this thing down to just, what is this, maybe 10 squares, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, yeah, it is. So if I were to chop it down to 1 square in length, the resistance of this thing would go down to, well, 1/10 of what it was before. All right. Now, as far as area goes, if I were to double the cross-sectional area of this thing, then that would also reduce the resistance because you're given more area for this stuff to go through. If I were to make it skinnier, then my resistance will shoot up. And so, again, look at that filament light bulb in your bathroom. That filament light bulb. I don't know if I can draw one. Little thing like that. Filament light bulb, got the little light bulb thingy. But inside, you've got something that goes up like this, something that goes up like that. Maybe there's 3 of them, but there's a really, really, really skinny, long wire that's right there. And what that does is that increases the length of that wire that current has to go through. And decreasing the area means that you're not only increasing resistance with the length, but you're also increasing resistance with the area too. All right. And so, again, this thing called resistivity, it is a property of a material. And what you should see is that based off length, it should be a pretty linear correlation between length. Same thing with area. As if you were to cut the area in half, I would expect the resistivity to double if that were to happen. But based off the temperature, that's gonna start to change things. And so experiments can be done to double check to see what happens to your resistance based on your changes in temperature. But this is a pretty short video. Just this is the main equation that you would have to know, and knowing that this is your resistivity property of material itself. That's going to be your cross-sectional area, and depends on your shape. You know, if you have a square that you're cutting off, then you just do base times height or length times width with that shape. I don't want to say length. Base times height. If you do a circle, pi r squared. If you know the length of it, that's what will go here. And usually as simple as that, but multiple choice questions would only have this, you working with the equation. Most likely there's going to be some kind of lab problem, which I'll try to make another video for that specifically, where you have this like Play-Doh that you've rolled out into this big long cylinder, and you try to find the resistivity of Play-Doh. And to find this, you would need to know the area, the cross-sectional area of the Play-Doh, and you'd have to start to change the length and find resistances based upon simple circuits. But this video comes before simple circuits, so I will stop here, and hopefully this is helpful on the very simple resistivity formula.